Alright, Dipto, welcome back to your tutorial. In this video, I want to explain to you how I figured out the cost function and the gradient. We have the formula for cost function given by j theta. This is equal to the average of this concave function. It's a concave function because we have the first part and the second part together, and when we have binary in outputs only, this becomes a cost function. Refer to Andrew's notes and you will understand what's happening there. Okay, now we see that the cost function formula has the ith output multiplied by the logarithm of the hypothesis subtracted, and from that we subtract 1 minus the ith output multiplied by the logarithm of 1 minus the hypothesis. What do you understand from here? You see that you need to know what the hypothesis is. The hypothesis was given in your sigmoid function. The hypothesis is a function of g which takes theta transpose x, and g itself is the sigmoid function. If you recall, you did the sigmoid function, which was here. Okay, which was here. Pretty simple, straightforward. Not going to go over that today. So we need to implement this in our cost function .m. Let's go and see how we have done that. Okay, what do we have as input for cost function .m? We want to find j, right? So for cost function, our inputs are theta, x, and y. Okay, now what else do you need? You need m. M is the length of y. Do you understand why that is the case? Because you have m number of training examples, and since you're finding the average, you have to divide by m. So in order to get this m, you use the same length of y. You could use length of y, and if you notice here, you also have m as the size of x. This is a different function, so your m here is going to be different. For convenience's sake, we just called m equals to length of y. We could have used m here as well, but I think it's better if you use m inside the function. Okay, now our initial j is 0. J, the cost, is going to be a scalar which depends on your theta, your x, and your y. If it is a scalar, the output you should get should not be a vector or matrix. It should just be a scalar. The question is, does this j that you calculated here, does this provide you with a scalar value? Okay, let's get to that slowly. Let's look at the equation on the left and we will have the solution on the right. The equation says that you need a hypothesis. Okay, let's call that hypothesis. What is the hypothesis? It is a sigmoid of x theta. What is x theta? X theta is simply matrix x multiplied by vector theta. Now, you saw here that this was theta transpose x. Why is this not simply written as theta transpose x? Because theta and x dimension, they have to match so that they can be a product. This here is for a vector. These here are for a matrix. I mean, x is a matrix and theta is a vector. So we should look at the dimension. X is 100 by 2. Actually, remember this. X is not 100 by 2. Here, you are going to have one more column added. So it's going to be 100 by 3. Let us update that. Let us go one more step further. Let me hit enter. Okay, and now if I hit Control C and if I hit US, okay, 100 by 3. See that? So x is 100 by 3 and your theta is 3 by 1. So if you were to multiply them, if you had your initial theta multiplied by x, see the dimension here is 1 and 100, that doesn't match. But here, if you have x times initial theta, the dimensions are 3 and 3. They match, which means you can multiply them and you are going to get what you need for your x theta. So theta transpose x actually is x times theta when we're writing in matrices. Andrew explained it. This is just me reminding you. Now we take the sigmoid of this. We already wrote the sigmoid function, which is here. It's pretty straightforward. once we have the sigmoid, we have the hypothesis. Fantastic. Now what do? Now we just calculate the cost. Okay, this looks a lot more complicated than this simplistic line written here. What's the deal? What's happening? Let's look at that. What is the deal? Nothing is the deal. What is the deal? Nothing is the deal. Oh, so many spaces. So many spaces. Well, while you're here, I'll just clean it up. I'll just clean it up. I'll just clean it up. Clean it up. By the way, hi Boishaki, if you ever see this. Anyways, now let us go back to what we have here. Our cost function is 1 over m. Do we have 1 over m? Fantastic. We have half the work done. Multiplied by a summation. You don't see a summation here. You don't see a for loop here. This is because this is a vectorization. What does vectorization mean? It means that we will perform a single line that will already do the summation. How does that happen? If you remember, when you have two matrices being multiplied, you do row and column, you do element by element, and then you add them up. Remember that? We can look at Andrew's explanation here. That would be pretty handy. Oh, well, Andrew doesn't have that there. Well, let me just show you what I mean. Dot product vector. Okay, we'll go images. All right. Well, not a dot product. Matrix multiplication is what we need. There we go. See, you see what's happening here? You go 1 times 10 plus 2 times 20 plus 3 times 30. Ah, there you go. That's the plus. That's the summation you're looking for. Fantastic, right? Okay, so we have the summation figured out through vectorization, but does this vectorization work? Now, you don't see a transpose here. Why do you see a transpose here? This is because, actually, let's step back a bit. Let's first put down log of h theta xi. Pretty simple now, since we have already a hypothesis, which is h theta xi, right? Which is x theta. And we had that run through sigmoid function. Now we get hypothesis. We take the log of that, multiply that with y. The only difference is this yi is not transposed, but this one here is transposed. Well, the reason is just to match the dimension. If you multiply y with log of a hypothesis, what would you get? See, y is 100 by 1, and your hypothesis is 100 by 3, I believe. I think so. Yeah, right. So x theta is, oh, do we even have that? Well, let's see how that has to match. It has to be 1 by something. 100 by 1. If you transpose it, it's 1 by 100. Yeah, it's 100 by 3. Yep, it's 100 by 3. Okay, so now your hypothesis is 100 by 3 and your y is 3 by 100. Okay, so 3 by 100 and 100 by 3. The 100 and 100 dimensions match. So the output is going to be 3 by 1, right? Yeah, I think it's going to be 3 by 1. Okay. Now let's continue. Oh, is it going to be 3 by 1? Make sure to check that later on. Anyways, now the same reasoning is applied here. In order to match the dimensions, we have the transpose here. So that should give us the cost, right? Matching the left to the right, essentially, other than yi, we use the vectorization. So here we have the transpose. Now, does this work? I think it does. So if we run x2 one more time, we want to check whether this is working. We'll hit enter. Okay, so see, our cost at initial theta is 0.693 and our expected cost is 0.693. So that works. And our cost at test theta is 0.218 and our expected cost is 0.218. Fantastic. We have gotten J to work. Now, we will look at whether the gradient, we can find the gradient. So this is where we have to be careful. We know from Andrew's notes that our gradient is going to be, you know what, let me show you from here. Quick 3, 2, 1, 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. Where do we go? We go for simplified cost function and gradient descent. Okay, we are not doing the descent yet. The descent would mean we would have to subtract the gradient from our theta. We are only interested in finding this much here, del theta j, a del of j theta with respect to theta j. We only want to find that much. The formula for that is given here. See, del of j theta of with respect to theta j. We only have 1 over m. We have 1 over m multiplied by the hypothesis, okay, minus yi times xji. Okay, so is the gradient working? That's the question. Well, yes, it does work, but the question is that xji and the hypothesis and minus y, why have they flipped? Simple as what we did for our cost. In order to match the dimensions, and when we are not using element wise multiplication, when we are doing matrix multiplication, we have to match the dimensions. So we need to shift the X matrix before the hypothesis minus Y matrix. Doing this matches the dimensions, and then we can get the gradient. Okay, if we continue with the program, we will see that our expected gradient is minus 0.1, and our initial gradient is minus 0.1. And you will notice that every single of our expected values match with the output that we got. So fantastic, you did this one correctly. And we will do the test one as well. Our expected gradients and our gradient that we found, they match. Okay, one mistake that you made was you skipped the parentheses here, which is why you got an error. I will recreate the error. So even though you have no syntax error, you will not be able to get the correct answer. So 28.14 and expected cost is 0.693. 16.41, expected cost is 0.218. You might have thought that this log means natural log, while Andrew was suggesting you use base 10 log. So let's use base 10 log just to show that that is not the case. Let me save this, go back to command window, I'll quit this one and I'll run x2. Here we go. Yeah, you are fine. And then we hit enter. See, 12.22, but you need 0.693, 7.13, you need 0.218, right? So this should tell you that this doesn't work. But check this out though, your gradient does work because, well, this is a different formula, right? So if you remember properly, just check your parentheses. Does this work? No, it doesn't, because this parenthesis, the third bracket on the outside, you are missing that. So here we go, one parenthesis here, one parenthesis here, save, command window, we will quit, x2 run, we'll close, and we will hit enter. There we go. Fantastic. All right, well done, Deepto. You have done up till cost function and gradient. Now you should move on to learning parameters using fmin_unc, unconstrained. Oh yeah, this whole thing here. This was for another video. Anyways, I am gonna sign out now. No edits, none whatsoever. I mean, nobody's gonna watch this anyways. All right, Boishaki, if you see this, bye.